This is a second example of optimization problem, and I've called this in my files and stuff the classic box problem. This appears as an example in your text. It says, and here's basically the idea. It says an open box is to be made from a 16-inch by 30-inch piece of cardboard by cutting squares of equal size out of, from the four corners and then bending the sides up. What size should the squares be to obtain a box with the largest volume? So let's take a look. I have an illustration here. So here we have the 16 by 30 inch piece of cardboard. We'd cut a square out of each corner, all of the same size, so that I could fold these tabs on the ends up along the dotted lines and make this into a box, tape them or something so that this is a box, and I want a box with the biggest volume. Let's look at this situation. I think it'll give us some insight. So here it is. What I have here is I have basically x, where x is the sides of these squares, and so I can adjust x. And then I have here a picture of the resulting box. All right, there, and then the volume. This says area here. I'm sorry, but I should have changed that. But it's really the volume. And so if I cut bigger squares out, well, I have a deeper box. It's not as doesn't have as big of a bottom, but it's deeper. And if I do that just right, I'll get the correct area, or I'll get the largest volume. And then if I continue, all right, well, again, then what's going to happen is then I'm moving to the place where notice there's not going to be very much of a box left because in one dimension it's going to be 0. So we'll have to keep that in mind, and what we want to do is we want to find this value, all right, where the area is as large as or the volume, excuse me, I should say, I'm saying this myself there, is as large as possible. Okay, so let's take a look. So again, what we'll do is we'll let each of these sides be x. Okay, and now let's see. We want to find the volume. We want to maximize the volume. So let's see. How do we calculate the volume of the box? Well, the volume of the box is the length multiplied times the width times the height of the box. I'll just say that this is volume. And now let's figure out what all of these are going to be. Well, the length of this piece of cardboard was 30 inches, but notice when I fold that up, this end up, it'll be x inches shorter, and when I fold this end up, it'll be x inches shorter again. So it'll be 2x inches less than 30. So this length is going to be 30 minus 2x. The width of the cardboard was 16 inches, but again, as I fold up each side, I lose an inch, or x inches. So the width will be 16 minus 2x. Okay, and the depth of the box, well, when I fold up this tab here, it's going to be x inches tall, so the height of the box will be x. So now I have that the volume, replacing all these, as a function of x, is going to be length 30 minus 2x times 16 minus 2x times x. Okay, now let's take a look at this. There are some limitations on this. Again, if I multiply this out, I'm just going to get a polynomial, so it's continuous. And the thing is, let's take a look at x. Certainly, x can't be any smaller than 0. If x were 0, we're not cutting any squares out of the corners. So x is going to have to be greater than or equal to 0. And now if we look at this, if x were 8, All right, then notice what would happen here. Then I'd be using up all 16 of these, all 16 inches here as the, with the flap. And so the box would have no width to it, okay? And we can see that if x were 8, the width would be 0. So the width has to be less than or equal to 8, all right? Or excuse me, x has to be less than or equal to 8, and I wrote 0 here. I'm sorry about that. Okay. All right, so we are looking for this, we're trying to maximize this on this interval. Remember that the maximum value will be either at one of the endpoints. X equals 0 will be the left endpoint. All right, at the other endpoint, x equals 8, or at critical points in between. And to find those, we'll have to take the derivative. And rather than multiply these all out, what I'm going to do is I'm just going to use the product rule. So I'll have 30 minus 2x, and I'll take its derivative, and then I'll have 16 minus 2x. I'll leave it alone, and times x, and I'll leave that alone. Plus, I'll have 30 minus 2x. I'll leave that alone. Then 16 minus 2x. Take its derivative, times x. Then plus, I'll have 30 minus 2x times 16 minus 2x times x, and I'll take the derivative of x. So in this first quantity, we'll have the derivative of 30 minus 2x is negative 2 times 16. Oops. 16 must have hit something with my knuckle. Minus 2x times x plus 30 minus 2x times the derivative of 16 minus 2x, again, is negative 2 times x. And then in back here, we'll have plus 30 minus 2x times 16 minus 2x times the derivative of x is 1. Okay, so let's see. So if I multiply this out, what will I get? I'll get negative 2x times 16. That would be negative 32x. And then negative 2x times negative 2x is positive 4x squared. Then I'll get a negative 2x times 30 is negative 60x. Then a negative 2x times a negative 2x is positive 4x. And then we'll have, as I multiply this out, I'll have 30 times 16 is 480. And 30 times negative 2x is negative 60x. Negative 2x times 16 is negative 32x. And then negative 2x times negative 2x is positive 4x squared. And if we look at this, let's see, what do we have? We're going to have a 4x squared, and then another 4x squared. I think I forgot the square here. And then another 4x squared is 12x squared. And then we'll have a let's see, a negative 32x and a negative 60x is a negative 92x. And then a negative 60 is a negative 158x. And is that right? Negative 152x, and a 30 is negative 184x. And then we'll have plus 480. And this, let's see, we want to set this equal to 0, so let me first of all take out a 12. I believe I can take out a 4. I guess it's a 4x, or just a 4, and I'll have left 3x squared. And if I take out a 4, 4 goes into 18 4 times, with 24 left, 46 x, and then 4 goes into 480 120 times. And I think that this further factors 4 times 3x. This should be negative minus 10. All right, times x minus 12. Let's just double check that. 3x times x is 3x squared, and 3x times negative 12 is negative 36x minus 10x is negative 46. That was negative 46x. All right, and then negative 12 times negative 10 is 120, so that's right. So notice then, setting this equal to 0, to get the critical points, remember the critical points are where the first derivative is either 0 or undefined. All right, and this one's never undefined, so it's only where it's 0. 4 is never 0. The 3x minus 10 will be 0 at 10/3, and the x minus 12 will be 0 at 12. Notice if we think about our interval here, this went from 0 to 8, that the 12 is outside of our interval, so we can forget about that. And what we have here is x, we have to look at these places. X is equal to 0, x is equal to 8, or x is equal to 10/3. And if x is equal to 0, let me remind us of what our function was. Our function was this. I'll just make a copy of it. Our function was this. If x is equal to 0, well, notice, of course, that if x is equal to 0, this term is 0, so v of 0 is 0, that we have a flat piece of paper because we haven't cut out any squares. If x is equal to 8, then 16 minus 2 times 8 is 0, so we'd get 0 for the whole thing. All right, and that's when we have completely cut off the ends, all right, as the flaps for this, so we got 0. And then if x is equal to 10/3, all right, I think that I have calculated that someplace, but I don't have it with me. I'll let you, I'll have to let you calculate it. I want to say this is around 729. That the volume is 729 and some changes, doesn't turn out to be exact. And I believe that that's that is the maximum amount. Let's take a look. Notice 10/3. 10/3 would be about 3 1/3, and this would be a little bit bigger than 3 if we were at this. I think I might be able to actually put in here 10/3, and when I do that, okay, when I put in 10/3, notice we're at the very top. I don't have the area, but it's around 729, and you can see that it's a little bit bigger than 700. So we have that result there. Okay. All right. So there's an example of an example of an optimization problem using calculus.